Page 98. Okay, let's have a look here at this now. Guys ready, yeah? Okay, so let's have a look. Let's say we have an example like in a race. Let's say you're looking at if the person can be first or first or second in the race. So let's say this one here is the probability that the person in the race finishes first. This one here is the probability that they finish second. And outside of this, and let's make this race easy. Let's say there's just 3 people in the race. Okay. So what would this number here represent? Well, that's not first and not second, so third place. There's 3 people in this race. Okay, so let's just write this down. It's a 3-person race, and we'll make it easier. We'll say there are no draws. So, you know what I mean, no draws. You finish the race and you're either first, second, or third. So I already know what number must be here. Why?
You can't
No.
have this, like, the first one to be just one.
Yeah, well, you can't win both first and second place at the same time, can you? You can't win gold and silver at the same time. You have this look about you that looks like trouble. It's my spider senses. They're telling me there's trouble over here. Is there any trouble? It's just my mistake? No trouble? Everything's good? Are you sure? Okay. So we know this is 0 because we can't win gold and silver at the same time. We can't be first and second at the same time. We can't be on time and late at the same time. So if this is A and this is B, we know that the probability of A and B is 0. This is called A and B are mutually exclusive. That's what this means. A and B are mutually exclusive. That they just don't happen at the same time. It's not possible. Now there's some things you already know which are mutually exclusive. For example, is it possible to have A and not A at the same time? No, you can't. It's like saying, can you flip a coin and get heads and not heads at the same time? No. So these are always mutually exclusive, always. But sometimes you have A and B are mutually exclusive events, which just means that it's impossible for them to happen together at the same time. Okay, so for example, another example would be each person's birthday will be on a different day of the week. So, you know, maybe your birthday this year is on a Monday and yours is on a Thursday or whatever. So in this classroom right now, what is the probability that nobody has their birthday on the same day of the week? That everybody's birthday is on a different day. So mine's on a Monday, yours is on a Tuesday, someone else's is on a Wednesday. What's the probability that everybody's birthday is on a different day of the week? Well, it has to be 0 because there's only 7 days and there's more than 7 people here. So somebody will have to have their birthday on the same day of the week, a Monday and a Monday. Now, two different Mondays, of course, but it's not possible for everybody to have a different birthday of the week. Okay, so this is another mutually exclusive. You can't have that as well. So that's mutually exclusive. Next thing to look at is independent. Any other examples? Okay, independent. So, just in normal English, what exactly does independent mean? If I am saying A and B are independent,
These statements are not relating to each other.
they're not what?
Relating to each other.
Yeah. So, in a probability way, what does that mean? So, I give you an example, okay? The probability so let's say A is the event that it's raining. So A is rain. So at the moment, do we have A or not A? I think at the moment we have not A for the moment, okay? And B is I flip a coin and it's getting heads. So clearly A and B are independent. If it's raining, that does not affect whether or not the B happens. Okay? But let's say B is the event that I am eating ice cream. Independent or not independent?
Not independent.
Not independent. Because if it's raining, it means I'm less likely to have ice cream, right? Maybe not in Ireland though, but you get the idea. So how can I make a statement about independence using probabilities? What do you think? So I want some way of saying that if A happens or doesn't happen, it doesn't affect the probability of B.
A has no relation with B.
Yeah, but how can I put that as a formula, a statement? Well, what about this? The probability that A happens, given that B has happened, is the same as the probability that A happens, given that B doesn't happen. So here what you're saying is your probability of A is the same, regardless if the B has happened or not happened. So this is what independence means. That the A probability is still the same, even if B has happened or not happened. Yeah. Now this formula can be simplified a little bit. So using the formula from earlier, this is probability of A and B over probability of B. This is the probability of A and not B over probability of B. Yes? Now, let me see if I remember the proof
Not
here.
probability of not B.
Oh yeah, sorry, of course, not B, thank you. Don't write this proof down until I make sure I remember how to do it. Probability of not B is 1. No, not B for the moment. I can change this to probability of not B and A. That's the same thing, isn't it? I mean, if you have the sets here, A and B, A intersect B and B intersect A, that's the same, right? So it's no problem if I swap those two around. Okay, now a little trick. Do I remember how to do this?
Do you use Go?
Huh?
it be...
I'm trying to get to a formula. I know where I'm trying to go. Just trying to remember how to get there. 1 second. A, B. I'll try. Let's see what happens. What's the worst that could happen? So if I put probability of A here and probability of A here, what does this represent here? This piece here I've circled. Probability of not B and A over probability of A. What's that? In green here. Probability not B given that A has happened times probability of A over probability of not B. Oh no, I see, no typing please. I said you don't have to write this down. It's not code for start chatting to someone online. Who are you talking to? Engineering student by any chance? Oh, of course not. Okay. You sure? Okay, good. Now here, not B given A over not B. Okay. I can change this into 1 minus probability of B given A times probability of A over probability of B. And this here is probability of A given B over probability of B. I know this is looking messy. Be patient. Yes?
The probability of...
Thank you. Over probability of B. 1 minus probability of A and B over probability of A times probability of A over 1 minus probability of B. Now it looks messy but it starts to simplify because if I multiply this in here, what do I get? Probability of A minus probability of A and B all over 1 minus probability of B. Probability of B, probability of A and B. Again, I know it looks messy, but let's cross multiply. Probability of A and B times 1 minus probability of B equals probability of A minus probability of A and B times probability of B. Now I multiply out probability of A and B minus probability of B times probability of A and B equals probability of A, probability of B, and then lastly here minus probability of A and B, probability of B. Something cancels though. What cancels? This one here and this one here. So you end up with this formula, probability of A and B equals probability of A times probability of B. I'm actually quite happy I managed to get there. So this is like the definition of what independence means. But this formula isn't a convenient way to check if they're independent. In fact, this formula is what is used to check if things are independent. If the probability of A and B happening is equal to probability of A multiplied by the probability of B, if this is true for your question, it means that A and B are independent. Okay, so let me show you an example. You don't need the proof, but you do need this formula here. This is a way to check for independence, if this is true. Now I'll give you an example, with maybe the example with the ice cream, for example. So we have here two events. rain and ice cream. So I don't know. Probability that it rains, we'll say is 0.2. So I'll put 0.1 here, 0.1 here. Okay. So maybe not 0.3, maybe put a different number. Oh, relax, come on. No big deal. 0.06. And here I'll put 0.24. And then on the outside, what's wrong, Albert? 0.06, 0.24, 0.1, and 0.654. Okay, so for example, what's the probability it will rain? It's raining. 0.16. And the probability that I'm eating ice cream, this is too high by the way, probability I'm eating ice cream, 0.3. Okay. And probability that it is not raining and not eating ice cream, 0.654. So on. So we want to check, are the events rain and ice cream independent? That is, does one affect or not affect the other? So what you need to check is the probability of rain and ice cream the same as probability of rain times probability of ice cream? This is, so I made this example weirdly to be independent possibly. 0.06. Does that equal rain is 0.2 and ice cream 0.3. Is this true or false? True or false? True. So this means they're independent events, which actually I think for Ireland is pretty true. People still eat ice cream if it's raining or not raining. So I think actually for Ireland it is true, if you've noticed this. So here is an example. Rain and ice cream are independent events, that having one doesn't affect having the other. Let's do another example, or let's do an example here actually. Okay, can I make up another example? We go down? What? 0.2? It's not. Nobody corrected me. It's not 0.2. Thank you, Albert. It should be, why don't you tell me? Yes? Thank you. Okay, now is it true or false? False. It's false. Why was Albert the only one who noticed that? Yeah, okay. Good. Okay, somebody is listening. Right, so this is false, so that means that, what does that mean for rain and ice cream? Rain and ice cream are not independent. Okay, that feels better. Yeah. We'll do another example. Can I go down? Yes? Okay. So a common example maybe would be something from biology. So there's maybe two diseases, disease 1, D1, and disease 2, D2, for example. So let's say that 1% of people have both diseases, okay? 3% of people have disease 1, and then how many people have disease 2? 4%. How many people don't have either of these diseases? How much? 24? 94, yeah. So we would like to check if disease 1 and disease 2 are independent, because, for example, in biology, some diseases, if you have one disease, it might make you more likely to have another type of disease. I cannot think of any examples, but there are things like, if the person has this disease, it means in the future they are maybe more likely to have some other disease. Can't think of examples where they go together. Yes, I know one. There's actually one in the news a couple of weeks ago. It was, I think it was,
Mental?
no, it was sexually transmitted disease, that if you have it, it makes you more likely to have cervical cancer. I can't remember, but you have this in biology where having one disease might affect your chance of having another disease. So it's important to know if they're independent. And there's a quick way to check. So we can check that these are independent. Probability of disease 1 and disease 2, what does that equal? That is 1%. Probability of disease 1 multiplied by probability of disease 2. That would be 0.03 multiplied by 0.04. That should be quite different, I would think. 0.0012. So because that is different, we think that these events are not, because it's not the same, not independent. Because this number here is not the same as this number here. You have this does not equal this, so they are not independent. So what does that mean? That means if somebody has disease 1 and you want to know what the probability it is that they'll develop disease 2, that is not going to be the same as somebody who doesn't have disease 1 and you want to know their probability that they'll develop disease 2. Now we haven't calculated this. Maybe having disease 1 makes you less likely to have disease 2. So I'm not saying anything about this. I'm just saying that they're not the same. That having disease 1 affects whether you will have disease 2. But I'm not saying anything about if it's more or less likely. But let's calculate it. So let's see, what is probability of getting disease 2 given that you have disease 1? Well, that's disease 1 and 2. That's 0.01 over 0.03, which is about 33%. What about the probability of getting disease 2 if you don't have disease 1? So what do I have on the top? Disease 2 and not disease 1. Disease 2 and not disease 1. What's that? 0.0. What is it? Disease 2 and not 1. It's 3, isn't it? Disease 2 but not 1. Yeah. And what's the probability of not disease 1? 0.97. This is much smaller, isn't it? Mm. 3% about only, roughly. So if you have disease 1, what's your chance you will develop disease 2? 33%. If you don't have disease 1, your chance of getting disease 2, 3%. So clearly they're not independent events. Having disease 1 greatly affects whether you'll have disease 2. Okay. Yeah, I think I'll just let you try some of these for a few minutes, and then if you want, let you try these for 10 minutes, and then for the last 10 minutes or so, I can answer any questions you might have from this chapter. Put the phone in the pocket. It'll make me feel better. Yeah, I feel much better now. Right, I'll let you try these for 10 minutes, and then if you have questions that you want me to do, I can do them as well. Is he asleep? Malik, try these for 10 minutes, and then after that I'll do some tutorial questions that you might have from this chapter. Okay? Alright.